Multiplicity of linear factors in polynomials. All right, graphs are going to behave differently at various different x-intercepts. Sometimes your graph is going to cross over the x-axis. Sometimes it's going to cross over the x-axis at the x-intercept, and then other times it's just going to touch and bounce off of the x-axis. Okay, we'll look at that in just a second. So let's talk about the behaviors at the x-intercepts. So if we have a polynomial that contains a factor in the form of x minus h raised to the p power, the behavior near the x-intercept is determined by the power p. Okay, so if we were to take x minus h and set it equal to 0, to solve for x, we would add h to both sides and we would get an x-intercept at h. Okay, so that's going to be a 0 that has a multiplicity of p, whatever this exponent is. All right, so the graph of a polynomial function is going to touch the x-axis. Let's go ahead and highlight that. The graph of the polynomial will touch the x-axis at zeros with even multiplicities. So if our exponent of that factor is even, the graph is only going to touch the x-axis. But the graph is going to cross the x-axis at the zeros when there is an odd multiplicity. So make sure you keep that in mind. Also, the higher the multiplicity, the flatter your curve is going to be at the 0. Okay, so if you think about this, if you were to graph y equals x squared in your calculator, you have a parabola. And at the same time, if you graphed y equals x to the 4th power, it would look very similar, but your graph kind of flattens out more at the 0. So keep that in mind, okay, this right here. Now, the sum of the multiplicities is the degree of the polynomial function, okay? The sum of the multiplicities, so when you add all of those exponents together, is going to end up being the degree of our polynomial function. So let's look at these values first, okay? We've got this function f of x equals x plus 3 times x minus 4 times x minus 1. Okay, so each of these factors has a degree of 1, or excuse me, a multiplicity of 1. Because we don't see an exponent there, they're understood 1. And if we were to multiply all of these binomials out, we would end up with x to the 3rd power. That would be the highest exponent, okay? So our degree is 3. Now our leading coefficient, again, if we were to multiply all of these out together, we would have a positive x times a positive x times a positive x. That gives us a leading coefficient of 1. The number in front of each of those x values is 1. We multiply them together, we still get 1. Now let's look at the zeros. If I take x plus 3, this factor, and I set it equal to 0 and solve, we would end up with x equals negative 3. And we see we have a 0 right here. Notice that its exponent, or its multiplicity, was 1. That's odd, so it crosses through the x-axis. Okay, then we take x minus 4. Set x minus 4 equal to 0. We solve and we get x equals positive 4. So we see right here our graph crosses the x-axis at positive 4. So we have a 0 there, and it's crossing because our multiplicity is, again, odd. Then we have x minus 1. So x minus 1, if you set that equal to 0 and solve, we get x equals positive 1, which of course is this 0 right here. And because its multiplicity is odd, the graph is crossing through the x-axis. Okay, now let's talk about the end behaviors. Because our degree is odd, we know our end behaviors go in the opposite direction, but we have this positive leading coefficient right here. So we have a positive leading coefficient, an odd degree polynomial. We know our end behaviors look like this. Positive leading coefficient means we start low, we end high. Okay, now let's look at our second function. F of x equals x minus 1 times x plus 1 squared times x plus 3. So again, I have zeros at x equals positive 1, x equals negative 1, and x equals negative 3. So positive 1, negative 1, and negative 3. However, we have something a little bit different here. We see that this x minus 1, or excuse me, x plus 1 term is taken to the second power. So our graph is only going to touch or bounce off of the x-axis. Sometimes when I'm drawing these out, I'll say, okay, I'll write the word cross, cross, above any 0 that has an odd multiplicity, or above any factor that has an odd multiplicity. But I noticed that this right here is taken to the second power. So this factor right here tells me that my graph is just going to bounce off of the x-axis right there. And hopefully you notice right here at x equals negative 1, the graph indeed does just touch the x-axis and bounce off of it. It doesn't actually cross through it. All right, now let's look at our degree. So I have to the first power squared and to the first power. Sum those up and we get x to the fourth power as our degree. And our leading coefficient is an x times an x squared times an x to the first power, which still gives us a positive 1 as our leading coefficient. Okay, so because our degree is even, and our leading coefficient is positive, we know our end behaviors are both pointing up. Okay, so I know I start high and I finish high when I'm graphing this polynomial function. All right, let's take all that together, put it together and see what we've got here. It says, given the graph, we're going to write a possible factored polynomial function, okay? We're going to write a possible factored polynomial function. So let's go ahead and talk about our x-intercepts. I see I have an x-intercept at x equals negative 3. So that means I've got a factor at x plus 3. Notice the signs always change. I have an x-intercept here at negative 1. So this is a factor of x plus 1. And then I also have a factor, or excuse me, an x-intercept at positive 2. So that turns into a factor of x minus 2. Now let's look at the behavior of all three of those zeros. This 0 right here, my graph just goes straight through the x-axis. So this is going to be an odd multiplicity, okay, like 1, 3, 5, 7. But if you notice that this graph is going straight through the x-axis, it doesn't flatten out at all. So we know it's probably going to be to the first power. So I'm going to go ahead and write the number 1 right there. Now my second x-intercept, or my second 0 right here, kind of flattens out a little bit, right? I can see that it flattens out right here. It's still cutting through my x-axis, but because it flattens out some, I know my degree probably needs to be higher than 1. So let's maybe call this to the third power. And then again, our last 0 right here, you can see it only bounces off the x-axis. It only touches the x-axis. It doesn't cut through it. That means its multiplicity needs to be even. And it's not a very flat curve right here. You know, it's not very wide. So it's probably only going to be to the second power. All right? So if we want to write this polynomial function, we could say f of x equals x plus 3 times x plus 1 to the third power times x minus 2 squared. Again, these two zeros are cutting through our x-axis. They're crossing it. That's why their multiplicities are odd. This one is only touching the x-axis. That's why its multiplicity is even. And the reason that we made this degree or this multiplicity higher is because the curve flattens out a little bit. Now this is a possible form of our factored polynomial function. Now we also need to talk about our end behaviors. Both of our ends are pointing up, right? So our end behaviors, or our degree, needs to be even. Our degree needs to be even. And not only that, if they're both pointing up, we know our a value, or our leading coefficient, needs to be positive. So let's check all of those out first. Is our a value positive? We notice when we multiply all these together, yes, we would indeed get a positive x value. Now our degree needs to be even. So the sum of all of my multiplicities needs to be even. 1 plus 3 plus 2 does indeed give us an even degree. So this is a possible factored form of our polynomial function. And of course, you can always check that using your Desmos graphing calculator. We don't have any other specific points necessarily labeled on this graph. I mean, I guess we could kind of eyeball this and see that this point appears to be located at 0, 12. We could plug this in for x and plug this in for y and solve for this invisible a value right here if we wanted to be more specific. But again, this is just a possible factored polynomial function. We just kind of want to inspect our polynomial behavior right now. All right, let's look at this next one. It says, given the graph, give the possible factored polynomial function. Okay, so I see right here that I have an x-intercept of -3, meaning that the factor would end up being x plus 3. And then I have another x-intercept over here at x plus, or at positive 5, so it would end up being x minus 5. Sign always changes, right? So if I look at this first x-intercept, I see how it is only touching or bouncing off of my x-axis. So I need my multiplicity right here to be even. And because it doesn't flatten out necessarily very much, we're just going to take this to the second power. And then I have x minus 5 as my other factor. And I see that it's crossing through my x-axis, so I know it needs to be an odd multiplicity. And again, it doesn't flatten out at all, so I'm probably just going to take this to the first power. All right, so we have f of x equals x plus 3, x plus 3 squared times x minus 5. Now, for this problem right here, I do see that I have a point that I could use to solve for an a value to help me with my leading coefficient right here. So if you use the point 0, 90, you can plug in 0 for x and 90 for the y value and see what happens. Okay, so f of x would be our y value of 90. And that should equal some a value. And when we sub in 0 for these x terms, we get 3 squared times -5, right? We would get 3 squared times -5. Okay, let's see what this gives us. We have 90 equals a, and then 3 squared is 9 times -5 is a -45. And then again, of course, solving for a, if we divide both sides by -45, we would get an a value of -2. We would get an a value of -2. So I could take this original factored form that we came up with and sub in -2 for this a value. So we get f of x equals -2 times x plus 3 squared times x minus 5. Now, again, the reason that we didn't necessarily do that for this first problem up here is because I didn't have any integer points that I could sub in to my equation and solve for a. This one I did. So right here, I think this would probably be the best factored form of my polynomial. Also pay attention to the degree. So this right here, this factor is to the second power, and this factor is to the first power. And when I sum those up, I get 3. That means my degree is odd. My degree right here is odd. That means my end behaviors go in the opposite direction. And I also see that my graph starts high and ends low, right? My end behaviors start high and end low. That means my a value needed to be a negative. And I see right here that when we solved for this a value, I do indeed end up with a negative a value. Okay, last example, it says, without a calculator, sketch a graph of the following polynomial function here. So we have f of x equals negative x plus 2 times x minus 5 times x minus 2 squared. So if I were to set each of these factors equal to 0, I see that I would get x equals negative 2, x equals positive 5, and x equals positive 2. Now, let's go ahead and place those on our x-axis. So I have an x-intercept of negative 2, positive 5, and positive 2. Now, what else is happening here? I can see that my first degree, my x plus 2, that factor has a degree of 1. That means my function will cross at this x-intercept. My second factor, x minus 5, also has a degree of 1, so my function will cross again. But at x minus 2, it has a degree of 2. That's even. That means my graph is going to bounce off of my x-axis right there. Also, I look at my factored form and I see I have a negative here at the very front. That means my a value is negative. So my a value is negative. And I see when I sum up all of my multiplicities, 1 plus 1 plus 2, my degree is even. So I know my end behaviors are going in the same direction, but I know they're both pointing down because my a value is negative. So I know I need to start low and end low. Now, from here, you really could sketch a graph just from this because, again, it says without a calculator and we are just sketching. So I know that my graph needs to start low, so down low. It needs to cross my x-axis at negative 2. Then it needs to bounce off of my graph at positive 2, and then it needs to come back and go back down right here. Kind of a wonky shape, I know, but this is the general idea. Now, if you want to get a better picture, you can always substitute in x values into your polynomial function to determine the height of these bounces, right? So let's do a couple of those, okay? Just very quickly. If we have f of, let's say, 0, when my x value is 0, so that would give me negative. 0 plus 2 would just be 2. 0 minus 5 would give us negative 5, and 0 minus 2 would give us negative 2, and then, of course, that factor would be squared. Again, all I did was sub in the number 0 for all of these x values. So let's multiply those together. Negative 2 times negative 5 gives me positive 10. Negative 2 squared is a positive 4. 10 times 4 is 40. So actually, the graph of this height is very high right there at x equals 0, okay? The graph of this height is very tall. So tall, in fact, that it's not even going to be on my coordinate plane. So if you wanted to right here, we could erase this and just kind of sketch a graph that goes off way up here, right? Now, if you want to see about the second peak of our graph, this second local maxima, we could figure out what's going on there. You can sub in 3, you can sub in 4. I mean, you could sub in both if you wanted to, if you have the time. Depends on how exact you want to be. But let's say f of 3. So now I'm going to sub the number 3 in for all of my x values. Right here, and right here. Okay? So we start out with a negative, and then 3 plus 2 gives me 5. 3 minus 5 gives me a negative 2. And 3 minus 2 gives me 1. So 1 squared is our last little factor there. Okay, so we have negative 5 times 2 gives us positive 10. And then times 1 squared, it just stays positive 10. So when my x value is a 3, my y value is a positive 10. So that part of my graph also should have been a little bit higher, but not quite as high as our other peak. So let's go ahead and draw something like that. Maybe a little higher, but you get the general idea, okay? So you can do that with all of your functions. Anytime if you want a more exact picture, you can substitute in as many x values as you want into your functions just to find multiple other points to help graph your function. And obviously I love using the Desmos graphing calculator. Our first example was this one right here, right? Actually, that was our second example. Our first example looked like this. It was our crazy little graph where the x-intercept of +1 flattened out. I'm sorry, the x-intercept of -1 flattened out. And that's why we decided to have a third degree, or a third to the third power. And then our last little picture right here is basically what we just graphed. So you can always use that if you would like to help check your work. Obviously, it said to do all of these things without a calculator, but I always like to verify when I have the chance. There you go.